formula of compound X is shown. So here's your skeletal formula, and he's asking which row is correct. The first thing is that they're looking for the molecular formula of X. Now to figure out the molecular formula, the skeletal formula is given in front of me, and I'm going to find the carbon atoms first. Remember, every point is one carbon atom, so that's 1, 2, 3, 4, 5, 6, and 7. So I know that it's got 7 carbon atoms. And the next thing is I'm going to try and figure out how many hydrogens are bonded with each of the carbon atoms. So this one over here, just complete the bonds. Each carbon atom must be making 4 bonds. So that's 1, 2, 3. That's 3 hydrogens with this one. This one has 4 bonds complete. Let's focus on this one. This one will have 2 hydrogens. This one will also have 2 hydrogens. This one will have 3 hydrogens. This one will have 3 hydrogens. And this in the middle has already got 3 bonds. So it's going to have 1 more hydrogen attached to it. So I'm not writing down the hydrogens. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So the number of hydrogens are 14. And there is clearly, obviously, one oxygen over there as well. So it's going to be C7H14 and O. So the correct options are going to be either A or B, because the other two have the incorrect molecular formula. The next thing is that they're asking you about the Fellings. They're asking you about the Fellings reagent, whether there will be a color change or not. So the first thing we're going to do is what is the Fellings reagent? Now I'm going to also identify what this molecule is. If you look at this molecule, it's a C double bond O in the middle. That's a ketone. So this one over here is a ketone. And we're going to try and figure out what will happen if there is a ketone and a Fellings reagent. Now, if you have a look at the reaction chart, here's your alcohol. Aldehydes and ketones, the Felling reagent is over here. Primary alcohols, they get oxidized to aldehydes, and aldehydes get further oxidized to carboxylic acid. Aldehydes, the C double bond O is at the end of the chain. They get oxidized by tolerance, Felling, or K2Cr2O7. Ketones, they don't have any further oxidation. So ketones are not going to react with an oxidizing agent like a Felling's reagent. Aldehydes would, but not ketones. So in this case, since it is a ketone, there's not going to be any reaction, and which is why no change. So the correct answer would be A. The following question reads, which statement is correct? So 2,2-dimethyl propanoic acid is an isomer of propyl methanoate. So now you can't really figure that out unless, well, you can actually kind of figure this out. If you can remember, propanoic acid, carboxylic acids, and esters are isomers, in fact, but they have to have the right number of carbon atoms. So what I'm going to do is I'm going to draw this one. The way I'm going to draw this one is this is clearly propanoic acid. So propanoic acid has 3 carbon atoms. So it's got 3 carbon atoms, and it's propanoic acid. So that's double bond O and OH. So that's propanoic acid. That's this part covered. The next thing is I'm going to draw 2,2-dimethyl, which means there are 2 methyls, both at positions 2. We can fill in the hydrogens. That's 3 hydrogens with this, 3 with this one, 3 with this one. So that's a total of 3 plus 2, that's 5 carbon atoms. The other thing is, the other one is propyl methanoate. So I'm going to draw that one as well. That's an ester. So it's an ester. So first thing is I'm going to draw an ester link. And if I draw an ester link, the ester link has prop on one side and meth on the other side. Prop on the single O side. Propyl is, so propyl is 3 carbon atoms, but it's going to be on the single O side. Methanoate, meth is on the double bond O side. That's 1 carbon atom, which we already have. And you can add in the hydrogens. That's 2 with this one, 2 with this one, and 3 with this one. So that's a total of 4 carbon atoms. This one is a total of 5 carbon atoms. So they're clearly not isomers because they have a different amount of carbon atoms. If they had the same number of carbon atoms, esters and carboxylic acids would have been isomers of each other. So let's try the next one. 2-methyl-butanediol is an isomer of hexane-3-ol. Hex, now that's an alcohol as well. And there's exactly 1 OH. So you don't care about that. Remember, alcohols, if they have a single OH, they would be isomers of each other if they have the same number of carbon atoms, which in this case, clearly, then they don't. Hex means the shortcut is, without drawing this, the shortcut is hex means 6 carbon atoms. Bute means that there are a total of 4 carbon atoms with a methyl branch, which is 1 carbon atom. So that's 4 over here, and the branch has 1 carbon atom. So that would give you a total of 5 carbon atoms. So these two would clearly not be isomers of each other. But just for practice, I'm going to draw hexane 3-ol, which is going to be 6 carbon atoms. Hex means 6. 3-ol means on the third one there's an OH. So 3-ol indicates that there's an OH. Butane 2-ol means 4 carbon atoms. Bute stands for 4 carbon atoms. 2-ol means there's an OH on the second. 2-ol means OH on the second carbon atom. And the second one, there's a methyl as well. So that's going to be 1 carbon atom. Methyl is 1 carbon atom. So clearly you can see that they're not isomers of each other. So let's focus on the other one. 3-methyl-butane-2-on is an isomer of pentanol. Aldehydes and ketones are isomers of each other as long because the ketone has acetyl bond O, but it's in the middle of the chain. An aldehyde has a acetyl bond O, but it's at the end of the chain. So they have the same molecular formula, but structurally they're different. Now, pent means 5 carbon atoms, bute means 4 carbon atoms, but there's a methyl branch that would give it 5 carbon atoms. So these two, this would be the correct answer because they would have the same number of carbon atoms, and aldehydes and ketones are isomers of each other. So you should be able to do this without actually drawing it, but I'm going to draw it just for the sake of understanding. Pentanol is 5 carbon atoms, and al means aldehyde. Aldehyde double bond O is right at the end of the chain. Butane 2-on, butane 2-on is 4 carbon atoms, and it's a ketone. 2-on means double bond O is in the middle of the chain on the second one, and on the third one there's a methyl. So this one, there's going to be a methyl over here. You can add in the hydrogens, but 5 carbon atoms, this is also 5 carbon atoms, and they would be isomers. You can count the hydrogens as well. There would be 3 with this one, 3 with this one, H, 3 with this one, 3 with this one needs 2, this one needs 2, this one needs 2. You can count the hydrogens as well, and they would still be isomers. That's 3 plus 2 plus 2 plus 2, that's 6 plus 3, 9 plus 1, that's 10. This is 6 plus 3, 9, 9 plus 1, that's also 10. So C is clearly your correct answer. And the last one as well, if you look at the last one, pentan 3-on, that means there's a ketone with 5 carbon atoms. If this one is also a ketone, a single ketone with 1 acetyl bond O, but it doesn't have 5 carbon atoms. Bute means the main chain has 4 carbon atoms, and there are 2 branches of methyl. That's 1 carbon atom and another carbon atom as a branch, and that would make it 6 carbon atoms. So they clearly have a different number of carbon atoms. So the correct answer is option C. Now let's try and do this question. We've got butane 1-ene and butane 2-ene, and they're treated separately with cold dilute acidified magnate 7 ions. And 4 students W, X, Y, and Z make statements about these alkenes and the diols formed from them. So bute 1-ene, bute 2-ene. So bute 1-ene, I'm going to draw both of them. Bute 1-ene is 4 carbon atoms, and bute 2-ene is also a total of 4 carbon atoms, and 1-ene means the double bond is on position number 1, 2-ene means the double bond is at position number 2. In both cases, what will happen is that the double bond would go away. So I'm going to rub off the double bond, and a diol will be produced. Remember, cold, mild oxidation produces diols. And in this case as well, the double bond goes away, and in that position, OH groups get added to it. So double bond bute 1-ene, this is bute 2-ene. So the question is about this one. The question is about the 2 students making the statement. So W, one diol contains 2 primary alcohol groups. So one of the diol contains 2 primary alcohol groups, which is not true. Like if I try and name these alcohols, this is a primary alcohol. Why? Because any alcohol that's bonded with the alpha carbon the carbon with the OH is bonded to just one carbon chain. So that's a primary alcohol. This one is a secondary alcohol because the carbon over here is bonded to on two sides by carbon chains. So that's a secondary alcohol. This one, both of them are secondary. Why? Because the carbon is bonded on both sides by carbon chains. Over here, the carbon is bonded on two sides by a carbon chain. So that's those two are secondary. So student number one is definitely wrong because you don't get two primary alcohols. So one diol contains a primary and a secondary alcohol group. That is true. So one of the diols, it does contain a primary and a secondary group. The other one, just remember that the other one contains both secondary. So, but student X is correct. One diol contains two secondary alcohol groups. That is also true. And both alkenes exhibit cis-trans isomerism. That's not correct because for cis-trans, but1-ene. So but1-ene over here will not work. This is but1-ene. That's 1, 2, 3, 4 carbon atoms. I've just drawn the double bond in the three-dimensional shape. So double bond is at the end of the chain, but it's not going to work. For cis-trans, you need both sides over here to be different and both sides over here to be different, which over here it's not different. So there wouldn't be any cis or trans because if you flip one side, it still kind of remains the same. So both alkenes are not going to show cis-trans isomerism. So the correct answer is X and Y. The following question reads that there's 2-bromo-2-methyl pentane and it's a tertiary halogenoalkane. So let's quickly draw this. So you've got 2-bromo-2-methyl pentane. So we're going to focus on the main chain, which is pentane. So that's 1, 2, 3, 4, and 5 carbon atoms. Pent is 5. And then there's 2-bromo-2-methyl. So methyl on the second one, bromo on the second one. So second one, bromo, and the second one is also methyl. Methyl is one carbon atom. Forget the hydrogens. You can fill in the hydrogens yourselves. That's clearly a tertiary halogenoalkane. The carbon is bonded, the alpha carbon, the one that's bonded to bromine. It's got three sides carbon chains. Now, which organic product are found when 2-bromo is reacted with a hot concentrated ethanolic solution of sodium hydroxide? So the first thing is we're going to look at the fact what happens to a halogenoalkane when it's reacted with hot concentrated ethanolic NaOH. So when it's reacted with concentrated NaOH ethanolic, elimination happens. Elimination is it turns back into an alkene. Halogenoalkanes will turn back into alkenes. So this is what elimination is. That the bromine is going to get removed and a hydrogen is going to be removed from the neighboring carbon atom. So one hydrogen will be removed and I've drawn the hydrogens now. One hydrogen will be removed from the exact neighboring carbon atom, which in this case would either be this carbon atom, so the H will go from this one and the double bond will be at this position, or it could be this hydrogen atom, the neighboring one, and it will be removed from this carbon atom and the double bond will either be at this position. This CH3 and this CH3 are equivalent. So if you remove an H from this one or you remove an H from this one, structurally it's going to remain exactly the same. So I'm going to draw both molecules that are going to be formed. Just remember, bromine gets removed and neighboring carbon atom H gets removed. And these two CH3s are kind of the same. So whether it gets removed from this one or this one, they're kind of the same. So I'm just going to pick one and I'm going to do that. So let's draw the molecule. So the molecule I'm going to get is 5 carbon atoms. And you either get a double bond over here or it's going to be 5 carbon atoms with, is that 5? Yes. And the double bond is at this position. So this carbon atom loses the halogen, double bond comes over here or it comes to the other one, or this, I mean, these two are kind of the same. So you're going to get these two molecules and all you have to do is you got to name them now. So 5 carbon atoms, that's a double bond on the second position. So that's pent 2-ene. Why? Because that's 1, 2, 3, 4, 5. So second one, and there's a methyl on the second one as well. So that's 2-methyl pent 2-ene. What is this one? This one is 5 carbon atoms and that's pent 1-ene. So this one is pent 1-ene. And there's a methyl group on the second one. The double bond is on the first one, the methyl is on the second one, so that's 2-methyl. So you're getting 2-methyl pentone and 2-methyl pentone. So the correct answer would be B. I think it's 2-methyl pentone and 2-methyl pentone. So B is the correct answer to this question. The following question is that polypropylene is an addition polymer. So, what are the CCC bond angles along its polymer chain? So, I'm just going to, for the sake of, I know that in a polymer chain, it's usually a saturated molecule. So they're all going to be 109 degrees because carbon would be sp3 hybridized. It would be making four bonds. It would be making four single bonds. It's going to be tetrahedral. So each carbon atom, when it's making four bonds, it's the shape of the carbon would be this one. But how did I reach that conclusion? So I'm just going to, for the sake of practice, I'm going to make a propene molecule. So what does a propene molecule look like? Propene is this thing. It's three carbon atoms, double bond, there's an H. So that's simply, and this one will have three H's. That's simply propene. Now, when you want to make a polymer, the double bond, make sure you don't draw anything on the right or on the left side. So what I'm going to do is I'm going to bend this a bit. And the way I'm going to draw this now is it's going to be drawn like this. The H's are in the right position, but this H over here will be, instead of drawing it on the right side, I'm going to draw it downwards. So that's going to be drawn downwards, and instead of drawing the CH3 on the left side, I'm going to point it downwards. So that's going to be my CH3, and there would be lots of propene molecules, lots of them. So I'm just drawing two, but there would be thousands of them. And the double bond is going to break, the double bonds will react, and the double bond will break. So this double bond will go away, and similarly this double bond will also go away, and they would end up forming linkages between themselves, and that's what a polypropene molecule would look like. But what you would notice is that it's now saturated. Carbon is making four bonds, and when it's making four bonds, it's going to be tetrahedral. The three-dimensional shape of the carbon would be tetrahedral, and in tetrahedral shape, in this shape, when carbon is making four bonds, when it's sp3 hybridized, four single bonds, the angles are 109.5 to be precise, but 109 degrees is sufficient. So the option is going to be A. And this molecular model is a good example of showing that each carbon atom, that's your CH3 coming out of it. That's kind of, the chain is going to be slightly, that's the molecular model. That's the actual three-dimensional shape where each carbon atom, when it's making four bonds, it's going to be tetrahedrally arranged. So the chain is not going to be just as neat and clean as shown over here. It's going to be, every bond is going to be at an angle of 109.5. And remember this, these are your structural formulas. These don't show the actual three-dimensional shape of the molecule. So anyways, we reached to the conclusion that option A was the correct option. 109 degrees was the correct answer. So this question is about an alcohol. So remember OH has a molecular formula C5H12O. So the molecular formula is given. It's C5H12O. It has several isomers. And he's asking which isomer has a yellow precipitate with alkaline aqueous iodine. So the first thing is, what is an alkaline aqueous iodine? Now, an alkaline aqueous iodine is basically NaOH with iodine, alkali with iodine. Is an iodoform test, and the test is specifically for these two functional groups. The functional groups are very specific. They have to have a CH3, which is next to acetyl bond O. I mean, it has to be exactly this structure exactly. Or it's got to be a CH3, which is next to, now we're talking about, the question is talking about alcohols. We're interested in this structure. So it's got to have a CH3, which is right next door to an OH, and the OH should be in this arrangement. With an H, the carbon will have an OH, and the rest of the molecule, this would either be a carbon chain or it's going to be a hydrogen atom. So what will happen in the iodoform test is, this molecule will give a positive, both these molecules will give positive results with the iodoform test, the CH3 would break off and it would form CHI3. It's going to be a yellow precipitate. And the other one is the rest of the molecule, this carbon over here, in both cases would turn into a carboxylic acid. But since the conditions are alkaline, you've added NaOH to it. Uh, the salt of the carboxylic acid is going to be produced, but we don't care about the reaction. He's just asking which alcohol will give a yellow precipitate. So this alcohol will give it has to have a CH3 which is next to CHOH and then the rest of the molecule. So coming back to the question, this structure over here is a must. I mean, the alcohol should at least have this structure over here. It should have a CH3 which is next to CHOH and then the rest of the molecules. So you've got 5 carbon atoms over here. So what do you do with 5 carbon atoms? That's the rest of the molecule. So 2 carbon atoms already accounted for. You're left with just 3 carbon atoms. So how many different ways can you accommodate 3 carbon atoms? That's either 1, 2, 3. 3 carbon atoms could be arranged in this manner. That's one. Or what you can have is, so the other one that you can have is that the carbon atoms could be arranged in a branch manner. 3 carbon atoms, so it's going to be 1, 2, and 3. I mean, that's probably the only possibilities. I don't think there is any other possibility. There are only 2 ways in which you can arrange those carbon atoms. It's either 3 carbon atoms in, remember it had a total of 5 carbon atoms, alcohol with 5 carbon atoms. So if you want an iodoform test, you need this thing. And the rest of the 3 carbon atoms could be arranged in 2 ways. So he's saying which isomer forms a yellow precipitate with alkaline aqueous iodine. So it's one of the 2. You could have although tried each one separately, but we just drew all the ones, and I'm going to try and name them. So this one over here is 5 carbon atoms, so that's pentane 1-ol. So this one is 1, 2, 3, 4, 5. Not 1-ol. The OH is on the second one, so let's correct that. That one is actually pentane 2-ol, which I don't think is an option. They've given pentane 3-ol, but not pentane 2-ol. Let's try the other one. The other one is 1. How many are in the straight chain? That's 1, 2, 3, 4. So this one is bute, and it's butane 2-ol. So it's 4 carbon atoms in a straight line with the OH on the second one. So that's butane 2-ol. And then there's a carbon chain on the third one. You're going to count from the side that gives a smaller number to OH has a higher precedence. So you're going to count from the side that gives OH the smaller number. So I'm going to count from this side. So this is butane 2-ol. And on the third one, there's a methyl. So that you got a methyl group, you got a carbon branch, 1 carbon branch on the third one. So it's going to be 3-methyl butane 2-ol. So option C is the correct option. So there are 2 ways of solving this one. You could have either tried each one of them and tried and figured out which one has this structure. Or in this case, I actually drew the 2 structures that will give a positive iodoform test. And we just simply figured out and named them. And I figured out that option C is going to be my correct option in this case. Let's try this question now. A compound X is heated at a reflux with aqueous NaOH. 2 products are formed, sodium ethanoate and hexane 1-ol. What is the compound? So the first very basic thing is that you need to know what happens. When you heat something in a reflux. Now all of them are esters. There's acetyl bond O and O. All of them are esters. And what happens is when you have an ester, this is what happens, that you got a double bond O and O. If you heat it, hydrolysis will happen with either it's alkaline hydrolysis or it's acidic hydrolysis. The double bond O side turns back into a carboxylic acid, and the single O side turns back into an alcohol. Now, in alkaline conditions, this would actually not be a carboxylic acid. The carboxylic acid would end up reacting with the alkali and it would turn into a salt of the carboxylic acid. So you have to be careful about that as well. So that is one important information. So we are going to move back to the question, and that's what I'm going to do. I'm going to try and heat each one of them. The double bond will break in all cases. So let's break the double bond. This side will turn back into an alcohol. This side will turn back into a carboxylic acid. So this one becomes double bond ONOH. This one becomes back. It turns back into an alcohol. I'm going to try and name them. Remember, there's no bond in the middle anymore. So the bond in the middle is gone. This one is 1, 2, 3, 4, 5, 6, 7, and 8. This one is octanoic acid. And this one is an alcohol with 2 carbon atoms, so that's ethanol. So anyways, that can't be your answer because he's looking for, in his case, it's hexane 1-ol and it's sodium ethanoate. And remember, it's not going to be a carboxylic acid, it's going to be a salt of the carboxylic acid. So make sure it's not going to be double bond ONOH, it's actually going to be a salt. The OH in the carboxylic acid is going to react. But anyways, that's not going to be the correct answer. Let's try this one. Let's get rid of the double bond. The double bond in the middle is going to break, so that's gone. This one will turn into double bond OH, but it will turn into a salt, so let's keep it as salt. And this one over here will turn back into an alcohol. So what alcohol is this? 1, 2, 3, 4, 5, 6, 7. So that's again heptanol. So that's not the correct answer. This one is ethanoic acid. So the salt would be ethanoate. So forget that, because remember, he's looking for a hexanol. So we need to give him hexanol. So this one kind of looks promising. So double bond, this bond in the ester link breaks. This one turns into an alcohol. This one turns into a carboxylic acid. But again, it's going to turn into a salt of the carboxylic acid. But again, we're wrong. The alcohol, that's an ethanol. Not correct. So clearly option D is the only one that's correct. So I mean, that's by default, it's going to be correct. The double bond or the ester link, not the double bond, the ester link will break. This one over here will turn into an alcohol, and it should be an hexane 1-ol. It's 1, 2, 3, 4, 5, and 6. That is correct, hexanol. And this other one is going to be your ethanoic. There's going to be double bond ONOH, and that would react, so it will turn into a salt. So that's sodium ethanoate, 2 carbon atoms. This one is hexane 1-ol. So D is going to be our correct option for this question. The following question reads, what is the major product Z of the following reaction? So you've got an alkene, a cyclic alkene. There's a double bond over here as well, and an HBr molecule is getting added. So I'm going to first discuss how do you figure out the major product. And the rule is, the Markovnikov's rule is, that the H in HBr will bond with the carbon that is already bonded to more H atoms. Or simply means that the H goes with the carbon that's bonded to fewer alkyl chains. So you've got a double bond, an HBr molecule is going to get bonded to this one. So this one clearly has fewer alkyl chains or more hydrogens. So the H would like to go, I mean, the double bond in the middle would go away. So I'm going to remove the double bond. It's going to become saturated. The double bond is gone. And the H will decide to bond with the carbon that's already bonded to more H atoms. So H will go over here and the Br will go over here. So the H likes to bond with the carbon that's bonded to fewer alkyl chains. This one is bonded to 3 carbon chains. There's only one H over here. This one is bonded to 2 carbon chains. There's already more H atoms on this side. And same goes over here. You got a double bond, and the double bond, look at the carbon atoms. This one and this one, the double bond would go away. So let's remove that. Carefully, double bond is gone. The H would like to bond with the carbon that's bonded to fewer alkyl chains. So the H goes over here, the Br goes on this side. So that's going to be your final product and major product. So Br should be with the top carbon atom. So it's either this or this. And this other Br should be in the middle carbon atom. That's so this one clearly looks like B. B is the correct option for this question. The following question reads that there's a structure of compound Q, which is a complicated structure. He's saying how many chiral centers are present in this molecule of Q. So for chirality, you would need four different groups. The carbon should be bonded. It should be tetrahedral and it should be bonded to four different groups. Only then could it have a chiral center. It would form two non-superimposable mirror images. So let's go and hunt for those chiral centers. So four different groups. So I'm going to eliminate the first. This one has three hydrogens, so that's clearly gone. This one over here has three hydrogens as well. That's gone as well. This one, the middle one, the two sides are the same. It's got a CH3, it's got a CH3 over here. So that is gone as well. This one is gone. It's not chiral because it's got two hydrogens. This one is gone because it should not have a double bond. That's an oxygen, wouldn't be chiral. This one is not chiral because it's got two hydrogens. This one is chiral because it's going to have one hydrogen and all. So if you look at this carbon atom, the one that I'm taking, that's this side is different, this side is different, this side carbon chain is different. There's an H that is added as well, so that is different. These two, then moving on, these two are not chiral. Two hydrogens with this one as well. This is going to be chiral because if you look, there's going to be one H with this. This side is different, this side is different, all four sides are different. So that is another chiral. So I'm going to put a tick mark over there. And then you have this one that's also chiral. There's going to be one H. So let me write the H for those. So this one has one H. All sides, they look different. If you're standing on this carbon atom, this side looks different, that side looks different, this side looks different. So all four sides are different, so that is also chiral. And the same applies to this one. This is going to be chiral as well. And this is not chiral because there would be two hydrogens. That's not chiral. These two, they look chiral because there's and this one is also chiral. So these are also chiral because if you stand over here, all the sides, they look different. If you stand over here, all four sides, they kind of look different. This one happens to be chiral as well. Because all sides, this side is different, this side looks different, this side is different, this side is different. So if you're standing on top of this, every side would kind of look different. These ones are not chiral because two H's, not chiral, two H's with this one, not chiral, two H's with this one, that's also not chiral. This one is also not chiral because it's got the same two sides. These N ones, so this is not chiral because, and the N ones are not chiral because they would have three H's. So they're not chiral. So the only ones that are chiral are, I forgot to put a tick mark on that. So that's a lot to take in. That's 1, 2, carefully 3, 4, and 5, 6, and 7. Did I miss anyone? Let me count again. It's 1, 2, 3, 4, 5, 6, 7, 7. These were not chiral. These were not, most of them were not chiral. So that's 7. So the answer to this is, okay, we didn't have any number bigger than 7. So the correct answer for this one is that it's got 7 chiral carbon atoms. Now, I'm just going to make a point over here as always think about chirality as a carbon atom having 4 different groups making single bonds. Only then will it have 2 non-superimposable mirror images. Like if you're standing on top, every side should look different. There should be different groups on all 4 sides. Now in cyclic structures, don't get confused. Like in cyclic structures, if you focus on this carbon atom, you would notice, like, think of yourself standing on this carbon atom. This side looks different from this side because this side has branches that are coming out, right? So it kind of, I mean, it's clearly different from that side. This side is different from the other side because it's got different things. I mean, the chains all look different. So this side, if you're standing on top of this, you're going to see different stuff over here. And there's an H. The fourth side is an H. So when you're standing on top of this, all four sides, they kind of look different. They're different things on all sides. So think of chirality in cyclic structures in this way. Anyways, you've got 7, so that's your correct answer. Now, this one is a question, organic question on infrared spectroscopy, and they're kind of easy questions. The infrared spectroscopy is given. What is infrared? Infrared is that different bonds in a molecule, they vibrate by absorbing certain frequencies from the visible spectrum, and every bond is unique, so they would absorb a different frequency from the infrared spectrum. Sorry. So what you have in front of you is an infrared spectrum, and you're being asked what could be the identity of compound X. So is it an ethanoic acid molecule, an alcohol, or a ketone, or an ethyl ethanoate? So that is what's given. Now, the first thing is whenever you have an infrared spectrum in front of you, you're going to ignore pretty much all the bonds. Look at this absorption over here. You got an absorption around the 1600, 1700 range wave number. Wave number is basically proportional to frequency. So there's an infrared frequency that's getting absorbed having a wave number is 1 over lambda. So that is proportional to frequency. So think of this acts as frequency, although it's not exactly frequency, but think of it as frequency. So there's an infrared frequency that's getting absorbed, and then there is this frequency getting absorbed around the 3000, 2500 range, and it's pretty broad. It's a broad absorption. So it's a pretty broad absorption. So what you're going to do is you're going to look at the infrared spectroscopy chart. Now here's a chart that is in front of you. And it gives you different wave numbers or frequencies of absorptions for different bonds. Now, the first thing is make sure you ignore all the other bonds. Don't care about the other bonds. Look for the serial bond or look for the OH because they're kind of very uniquely identifiable. There's going to be a strong, this is the appearance of the peak, there's going to be a strong absorption in the 1600, 1700 range. And for the carboxylic acid, that's kind of very easy to detect. If there's an OH bond that's vibrating and there is a carboxylic acid, there's going to be a strong and very broad absorption in the 2500, 3000 range. So a pretty strong absorption in that range. So look for these two bonds first. Now, if I go back to the question, if I go back and have a look at the question, you would notice that it's got two things. It's got, this one is clearly an OH peak that belongs to, so it's an OH peak of carboxylic acid. And this one clearly is the serial bond O peak absorption. 1600, 1700, that's what we saw. So remember, always focus on these two peaks first. Try and find out, because it's very hard, infrared spectrum, pretty hard to actually figure out bonds, but you can always uniquely identify serial bond O, and you can also identify OH groups. So if I go back to the question, the answer is clearly ethanoic acid because it clearly said that there was an OH that belonged to a carboxylic acid, and there's only one carboxylic acid that's given, so the answer is going to be A. Because if it's ethanoic acid, it's going to have both types of bonds. It's got a serial bond O and it's got an OH that belongs to the carboxylic acid as well. So A is the correct answer. Now this question reads that which reaction produces an organic anion with a good yield? So an anion, a negative ion, which is going to be having or giving you a good yield. So the first one is heating ethane nitrile under reflux with dilute NaOH. So what's going to happen in this case? So let's go back to our chart and let's focus on nitriles. Nitriles are what happens when you have a nitrile like this over here. You heat it with NaOH or reflux, hydrolysis happens and it turns into a carboxylic acid. It will turn into a carboxylic acid, but since the conditions are alkaline, the carboxylic acid would end up reacting with it, and you'll get a salt of the carboxylic acid. So let's draw ethane nitrile, that's C111N. This one will have 3 H's. You heat it under reflux, it will turn, the CH3 will decompose, C111N will decompose or hydrolyze, and it will turn into a carboxylic acid, but it will give a salt of the carboxylic acid because the conditions are alkaline. So you will get an organic anion in that case, and that pretty much makes sense. It makes good sense. So that one is definitely correct because you're getting an organic anion, and it's going to be good yield. The other one, if you do acid hydrolysis, something similar would happen. So this is NaOH and reflux. In acid hydrolysis, something similar would happen, but it won't give us salt. It won't because in acid hydrolysis, the carboxylic acid formed will not react with the acid. It will just be carboxylic acid. So it's not going to give you an anion. So with sulfuric acid, you're going to get a carboxylic acid, but not the salt or not the anion. Alkanes have no reactions with metals. They pretty much have no reactions, just a few reactions. Ethanol with NaOH, again, it's not going to be ethanol, or alcohols are not acidic. They only react with very reactive sodium metal. So the correct answer is going to be option A. That's A. In this question, you've got in which of the following reactions is the organic compound oxidized by the given reagent? So he's talking about oxidation. So it's got to be oxidized. So the first one is this compound over here is an aldehyde. So I'm gonna first look at an aldehyde, and if you have a look at aldehydes, aldehydes over here, aldehydes, they do this part over here. Aldehydes, this is aldehydes. Aldehydes, they do get oxidized by tolerance, Fellings or K2Cr2O7, and they get oxidized to a carboxylic acid. So aldehydes do get oxidized. And how do you identify it's an aldehyde? It's got to have a CHO. So this one, number 2, is definitely correct. This one is also an aldehyde, and it's got CHO at the end, so that's serial bond O right at the end, and it will get oxidized by a Felling as well, just as we saw a few moments ago. This one, number 1, is nucleophilic addition. It's not a redox reaction. So nucleophilic addition is that if you have a carbonyl compound, it's got serial bond O, ketones or aldehydes, if you add HCN, you get nucleophilic addition. And what happens is that carbon that was previously making a double bond with oxygen will now turn into an alcohol, and it will have a CN attached to it. So this is not an oxidation reaction. This is known as nucleophilic addition. So option number 1 is definitely incorrect, and that would make it the correct option would be C, according to the marking key. C stands for 2 and 3 being the correct answers. The following question reads that when the apparatus is set up as shown, an orange precipitate forms in the test tube Z. So this one. Now 2,4-DNPH, this compound over here is a test for. So this one is a test for carbonyl compounds, aldehydes and ketones. So if you're getting a positive test with carbonyl compounds, that definitely kind of means it's an aldehyde or a ketone. And over here, what you're doing is this compound Q, and that's being reacted with potassium dichromate 6. So if I look at my chart, I know that it's definitely an aldehyde or a ketone, one of the two, and K2Cr2O7. So, or KMNO4, both of them, when you reflux, the alcohol turns into either a ketone or an aldehyde. It can be a primary alcohol. A primary alcohol will turn into an aldehyde, or it would be a secondary alcohol that would turn into a ketone. Either one of them, orange precipitate with 2,4-DNPH, dinitrophenylhydrazine, that's going to give you an orange precipitate. Now for aldehydes, the reaction does not stop here, because With KMnO4, it's going to get further oxidized to a carboxylic acid. The reaction stops for ketones, but aldehydes will further get oxidized to carboxylic acid if you don't stop it. The way you stop an aldehyde is that you quickly remove it, you need to distill it. Now, if you look at the apparatus quickly, then in the apparatus you would notice that even if you have a primary alcohol, it will turn into an aldehyde and the aldehyde would quickly evaporate and leave instead of turning into a carboxylic acid. So both options could be correct, that the molecule that's coming in could be a primary alcohol, it could be a secondary alcohol as well, because you're not refluxing it, because reflux means that nothing would be able to come out, but the aldehyde, if it's formed, it will quickly evaporate and it will reach the other end. So that would prevent oxidation. So you could have a primary alcohol, you could also have a secondary alcohol. So this one over here is a primary alcohol, because the OH over here is just bonded to one carbon chain. I mean the carbon, the alpha carbon, the one that is bonded to OH is bonded to just one carbon chain. This one, so this one is primary alcohol, while this one is our secondary alcohol. Because the carbon, if I draw this molecule, look at the central carbon atom, there's a CH3 first. Then the second one is a carbon with H and OH. So I got a carbon with H and OH is in brackets, so that's a branch, and then followed by a CH3. So focus on this carbon atom, it is a secondary alcohol. This last one is definitely a tertiary alcohol. Tertiary alcohols, so that's a tertiary alcohol. They don't undergo oxidation, so they won't have any oxidation product. So that is wrong. And how do I figure out that that's a tertiary alcohol? Because if you look at this carbon atom, it's bonded to OH and it's bonded to 3 carbon chains. There's CH3 3 times, so that means there's a CH3. Then there is another CH3, and then there's a third CH3. So that is, this carbon is a tertiary alcohol. So they don't undergo any oxidation. So it's got to be a primary or a secondary alcohol. So 1 and 2 are definitely correct, and that would give me as A as my option. Now this question is an easy one. There's he's talking about chlorofluoroalkanes, which are basically CFCs. These are inert, unreactive solvents or volatile substances which are frequently used as refrigerants, coolants. It's used in anesthesia, used as solvents. So they're a very important class of chemicals, and they diffuse into the stratosphere and broken down by ultraviolet light. Now what happens is that when you have ultraviolet light, and if you have a CFC molecule, let's say I have a simple CFC molecule, the Cl bond is very susceptible to UV light, and this bond will break into pieces, and that would result, and it will homolytically break. The bond will break equally when ultraviolet light and Cl bond. Remember, Cl bond or maybe bromine, but in this case he's talking about the CFC, so there is no bromine. So Cl radicals are produced, and the Cl radicals are then involved in ozone depletion. What they do is that they are short of one bond. A radical is a very reactive species because its bonds are not complete. So they react with ozone, and when they react with ozone, they break it down into O2 molecules, and a ClO radical is produced. Again, this is a radical because the oxygen bonds are not complete. The ClO radical then goes and reacts with other ozone molecules, O3, and what happens is it breaks down again into O2 molecules, and as a result another Cl radical is produced. So ozone depletion is caused by Cl radicals, by chlorine radicals. The CF bond is pretty strong, so that's not broken. Alkyl radicals don't play a role in that as well because they don't react with ozone. So it's usually the chlorine radical which are very reactive, and they end up. So the simple answer to this question is that chlorine radicals are the ones that are responsible for ozone depletion. Now this question states that a mixture of 3 isomers of C2H2Cl2, they're polymerized, and which sequence will be seen within the polymer chain. So first thing is, let's focus on the three isomers. What are these three isomers? C2, H2, and Cl2. So I'm going to start off with the first one. So it's definitely a double bond C2, H2, and there's going to be Cl2. So that is one structural isomer. And then there is the other one, which is that the two Cls would be on the same carbon atom. And that's about it. Structural isomers, that's it. But one of them is going to make cis-trans isomers. This one over here, this double bond over here, is going to have cis and trans isomers because the carbon over here, the two sides are different, and the carbon over here, the two sides are different. So here I'm showing the two stereoisomers or geometric isomers, cis-trans isomers of the same molecule. That's the three-dimensional shape, which is that either the two H's would be pointing in the same direction, or what will happen is that the H atoms would be pointing in opposite directions. But when you're making a polymer, it doesn't really matter. This thing, whether you're making a polymer out of this or you're making a polymer out of this, it wouldn't really matter. So let's try different combinations of the polymer. First one, remember, these are the two monomers that I'm going to use. And let's try and figure out what type of polymer could be formed with either of them. So the first one, this one, let's try and do that. Remember, let's try and draw the repeat polymer. So here you can see the three. I've just drawn three repeat units. But also remember that what can also happen is that the repeat alkenes are not going to be in the same order or sequence. Maybe they're also upside down. So let me draw one of them as flipped around. So let's do that. Let's put it upside down. Just imagine the carbons are straight, but it could arrange in this manner as well. And the double bonds, what will happen is that the double bonds would break in the middle. So they would be gone. So all these double bonds are gone. And the polymer chains can link up. So let's say there's a link here, and they would link up in this way. So that is one sequence that could be obtained. And let's do the exact same thing with the other one. Let's try and do that. So that's one sequence that could be obtained. And let's repeat this with the other sequence. The other one is this one. So I'm just going to copy a bunch of, so that's one example. So that's one. And let's try and copy more of them and create more copies out of it. That's another one. Maybe there's another one, but that one is upside down or flipped around. So that could be another one. And so is this flipped around? So that kind of looks flipped around. I'm going to get rid of the double bond in the middle. So all the double bonds are gone. And all of these would link up, and that's going to be my chain. So remember, the sequence can be upside down as well. So anyways, so if I go back and have a look, he's talking about this one. Okay, can we get this thing? So is that part of a section of the polymers that we have drawn? So let's go and have a look. So there is the two Cls, and there's this Cl which is at the bottom. Now this one over here will be possible, but it will only be possible if something like this happens, that that one of this copy that and it connects. Let's assume that it connects. So what will happen is that there would be two Cls on one carbon atom, and the next door there is one Cl. So that is a possibility, this one, that there are two Cls. So there are two Cls. I mean, this one, let's highlight that. So there are two Cls on the same carbon atom, and on the next one there is one carbon atom. So that is a possibility. So this one, it definitely looks correct. What about this one? Is this the section of the polymer? So two Cls at the bottom, so that is a possibility. So if we go back, you'll notice a chain where there are two Cls. So this one over here, that section over here is present. So that is also Also quite fine. What about this one? You got only one Cl and the other one is two hydrogens. So is that a possibility? So you got two Cls. So there's only one Cl. And on the next one, there are two hydrogen atoms. So that is also a possibility. And how is that possibility? Let me remove this section, get rid of that, and maybe connect this one. So let's say I cut this out and I join this with this one. So you would notice that there's on one carbon atom there's only one Cl, on the next one there is two hydrogens. So that is a possibility, that on one carbon atom there is only one Cl, and the next one there are two hydrogens. So that is also a possibility in the sequence. So all three are kind of correct. I mean, what you can do is you can, these were your initial starting monomers, and you can sort of mix and match them and try and figure out how many different arrangements are possible in the polymer chain. So in this case, it seems